Hello and good afternoon, everyone. I'm Haijun Xia. I'm assistant professor at Cogsci and Design. This quarter, I'm co-organizing this Design Large talk series with my colleague Jim Holland. And if you have any questions about the course, Brian, with your hand, that's our TA. Go to Brian. So it's my great pleasure to introduce Rubaiat Habib. Rubaiat right now is a senior research scientist at Adobe Research in Seattle. And we first met exactly almost 10 years ago when Rubaiat was a research scientist at Autodesk Research in Toronto, Canada. And I was a graduate student in University of Toronto. And we hang out many times in Toronto. We presented papers together in the same sessions of the conference. And we struggled with AV problems together in one of the sessions. And what I realize now after struggling with so many AV problems is I realized that the ultimate technology frontier is not AI, it's really AV. So glad we have everything working today. So Rubaiat's research is in the intersection of HCI and graphics, doing amazing work about how to support people's creativity, design, and art, and storytelling using technologies. And some of his work has been turned into actual product that are used by millions of designers and artists. And notably, Sketchbook Motion has been or was recognized as the best iPad app of 2016 by Apple. Rubaiat is also an artist himself. He creates all kinds of arts in the form of animations, drawings, and comics. And one of the most notable artifacts, or the art piece, is his PhD thesis. So unlike my thesis and many other theses that are in boring text and tables and charts, his PhD thesis is a comic book. So I encourage you all to check it out. And I'm confident that today's talk will feature some amazing art. So in this talk, Feynman's Purple Stylus, Rubaiat will take us through a fictional story of how AI will help Richard Feynman, the really renowned theoretical physicist, to rediscover the breakthroughs that fundamentally transformed theoretical physics. Let's welcome Rubaiat.
Thank you for the kind introduction, Haijun, and I'm super glad to be here and excited to share some of the ideas with all of you. So as Haijun mentioned, today's talk is all about tool building. And tool building is inherent in our DNA. We have been building tools for hundreds of years, tools like language and graphs and mathematical notations. These are cognitive tools that significantly enhances the way we communicate with others, see, and ideate. Now, how would tools like these evolve in 20 or 30 years? What kind of tools will creators like scientists, artists, designers create with AI? We don't know. But maybe we can have a conversation about how the process would look like. What are the great characteristics of some of these great cognitive tools? So to ground our discussion, let's talk about a very specific tool today, as Haijun mentioned, Feynman diagram. Introduced first in 1948, Feynman diagram actually talks about how subatomic particles like electron and proton interact with each other. It's a pictorial description. And before the introduction and invention of this tool, theoretical physicists always used very complex mathematics to do the computations. So it was very hard to understand, very hard to calculate, compute. But since the invention of this specific cognitive tool, it literally transformed the theoretical physics, the entire field. It made things easy to understand and accessible. It was adapted in many other domains, even as the field evolved with new particles and new theories. And it was not just a pedagogical tool that is easy to understand. It was a powerful tool for competition. As Nobel Prize winner Frank Wilczek mentioned that his Nobel Prize winning calculations would have been unthinkable without Feynman diagram. So as an HCI researcher, as I've been reading the history of this diagram and how it evolved, and what are some of the challenges it faced in the earlier stages of its lifeline, it really helped me think about, we can look at the history and project about how future could look like and what would be some of the great characteristics of future tools and representations. So lately, I've been thinking a lot about what if Richard Feynman would reinvent his tools in digital medium with the powerful AI assistance. So that is pretty much the backdrop of today's story, Feynman's purple stylus. So some disclaimer here, I'm not a theoretical physicist. So the artifacts I'm going to show today are pretty high level, and it's not dive deep enough into the theoretical physics to use it in actual applications. But really the focus of the talk is talk about the interaction and AI's role into it. And also this is a work in progress, so I'd appreciate your comments and feedback from everyone as well. All right, with that, let's invite today's primary guest, Dr. Richard Feynman. So I'm a great admirer of Richard Feynman, and I've been seeing many of his interviews. I'd have really loved to have an interview with him today and talk with him, have a podcast, but today, given the time constraints, we will get right into the laboratory. We will do an experiment. So here is how the laboratory looks like. We have given this digital whiteboard to Richard Feynman and a stylus and a powerful AI tool indicated by the yellow bubbles there. So we will ask Richard Feynman to reinvent the tools in digital medium and to do it with the use of AI. So we will go through the process and talk about the process in 3 sections. So Feynman diagram was invented almost 70 years ago, and one thing to note was it was invented in a static medium, pen and paper. So the first reaction of Feynman is that he redraw what he did in 70 years ago. So if you look at the top left picture, it's actually 2 particles interacting with each other. One electron coming close to each other and then releasing some energy on neon, and the other particle is absorbing it. The second figure is all about a particle electron that is moving but releasing the energy as it is moving. So when I first saw the picture, I felt like, okay, this is interesting. I mean, at that time, this was revolutionary because they call it space-time diagrams. So it's a significant leap, moving from complex mathematical expression to a pictorial representation like this. So that's why it's called space-time diagram. But when I first saw this picture, I felt like Richard Feynman must have thought something different in his mind, something a bit more dynamic and vivid. But because it's a static medium, he has to represent this T in a T dimension in paper to show how things change over time. So I'm not the only one with that thought. The powerful AI also had the same thought. And because this AI is antagonistic, check out this related work, in nature, that means that it is really combative. It asks difficult questions in the inception of its design. So it is really forcing Feynman to think about, to leverage the affordances of digital medium like animation and interactivity to explain the diagrams or to make the diagrams more easier to understand and use. All right, so Feynman has a challenge. He has to rethink his diagrams now. So let's give him some space, let them figure out what to do the next step. But meanwhile, let's talk about something else. You know, almost 10 years ago when I went to SIGGRAPH, SIGGRAPH had a really nice book stall with amazing books of art and animation. I encountered this book called Elemental Magic. It's a fascinating book. It's one of my favorite books if you're really into animation. So this book is written by Joseph Gilland, a very famous Disney animator who used to draw special effect animation in paper. These are all hand-drawn. And this book is a step-by-step illustration of how he drew all his fire and fluid and magic and explosion animations. Now, this book is fascinating because it talks about the technique. And these techniques are not inspired by physics, but they are not physics. They are an approximation of the physics. They are powerful because he can control it, stylize them, exaggerate them. If you look at the Disney animations, even the fire and the fluids have certain characteristics, right? They have the villain nature. So you can't do it with physics. And he made a very interesting comment. I will get back to that later. Jim and I talked about it a little bit. He said that because he had pen and paper, his imagination was not limited by the digital tool or digital tools designed by others. So that's really motivated him or inspired him to create this new tool, which he developed to control and design all these special effects. So I was fascinated by it, and obviously my first intern as a researcher was worked in this space. Junxing, excellent researcher, and we started working on different fluid simulation. One of my co-author Yosh Stem had some excellent fluid simulation work, but it was a really challenging problem. We had no idea how to control the fluid simulation, a classical challenge in computer graphics, how to control physics, right? But at that time, I remember Yosh Stem pointed out this really interesting paper back in the 1990s. This paper is all about how can we approximate fluid simulation, complex fluid simulations, with these atomic particles, or we call it flow primitives. So it's very interesting that how something as complex as fluid simulation with complex mathematical expressions can be broken down and approximated with these simple flow primitives. So that design motivated this paper really motivated the design of our papers. So here is the interface. You can see in this interface we had a set of flow primitives. So you have these flow primitives. For some reason the video is not playing here. Let me try again. Yeah. And then each of the flow primitives has their own energy fields. Again, the video is having trouble here. And as I put more drawings into it, you can see how the drawings are deformed over time. Okay, looks like it's really not liking the video is being paused automatically. But you can get an idea how things work here. But the interesting thing is, as you change the parameters, you can see how their effects change over time. For instance, as I move the particles, as I move the brush, you can see how it affects the drawings. Here is another example where we take a simple flow primitive and use an example drawing there. And then again, as I add more and more brushes, you can see how we can create more complicated drawings. So I hope you will use your imagination to imagine how the video would look like. But here is the key idea. As you mix more and more brushes with each other, you have an intuitive understanding about how things work. Now, what's interesting in one of the parallel of this problem with Feynman diagram is that we are not trying to simulate reality. That's what not Feynman tried to do. Feynman tried to simplify the problem by those primitives, the different types of particles, electron and proton, the type of energy they release. But in practice, they are not discrete particles. They are like kind of energy fields. But in order to make things simpler and easier, he had to invent those primitives so that we can do the calculations. But the primitives can be malleable as well. In this case, one of the artists designed this specific primitive, flow particle, that changes over time. And because it changes over time, you can create complicated effects like fire, for instance. So we have seen how like simple primitives can help us to understand complex phenomena, how those primitives can be made, simple primitives and abstraction can be made malleable so that users can repurpose it and create complex phenomena. But the most important thing is, as a user, as you play with the primitives, because it's interactive, as they interact with each other, you develop an intuitive understanding about how things work. All right, so let's get back to Feynman and see what he's doing. All right, so looks like he created animated version of the two diagrams above. So you see it's something very simple. That's exactly what the static diagram depicts. Two particles that are coming close to each other as they're emitting photon. The other one is observing it. In the right one, as an electron is moving, it is absorbing. So it's the same representation, but using digital media. But that is not enough for Feynman diagram, because in the theoretical physics, there are many different types of particles, and they exhibit different behaviors and different energies. So in practice, there is this set of rules and possibilities and interactions happening. So for instance, they need to conserve energy and momentum. There are certain types of particles, there are different types of energy, and not all particles interact with each other. So how to capture all these things, all these rules and theoretical knowledge we have in physics in this specific diagram? Feynman doesn't know programming, but looks like we need to do something like simulation. How can he do that without simulation? So Feynman is going to have a conversation with the AI, and we will take another detour, talk about something else, and get back to Feynman to see what he has done. All right, so while Feynman is talking about simulation, let's talk about this paper you just presented last week with Haijun Chia. This is a collaboration. So this paper is all about how can we create interactive simulation with sketching and drawing. So there's no programming required. It's all about user is drawing a few lily pads and a frog, and then through speech he says this frog hops to a lily forever. That means that creates a for loop to create an interactive simulation. And then you can say the butterfly follows the frog. The system knows that is the sketch of a butterfly, and then you can see the system acts accordingly. So this is kind of a small simulation here. So I don't know whether the video will play or not, but let's try and see what happens. As you mentioned, AV problem is bigger than AI problem, okay? So let's see.
And this is a ball.
It's playing.
And I'm going to draw some water too. Lastly, I'm going to draw myself a dog. Draw myself a dog. Over and over, the boy throws the ball into the water, and then the dog gives the ball to the boy.
Okay, so in this case, you can see the sketches are labeled, and the animation is not playing, unfortunately. But let me see if I can pause it and then play the
I'll make it interact with the windmill somehow.
Okay. So you can see that, here, as soon as I say it over and over, the dog brings the ball, it creates an...
For 0.2 seconds, and then water moves down for 0.2 seconds.
So this is an interactive
Now I have a little bit of
simulation.
an effect there. Great.
So let's take a look at another example here.
And these are the blades. And I'll make it so I attach the blades to the windmill. This is wind. And I'll make it interact with the windmill somehow. I'll save it using the save button. When wind collides with blades, blades rotate. Great, it works. Oh wait, it's still going. I can fix that. After wind collides with blades, blades stop rotating. This is a switch. This thing is static. And I'll make a wall. This wall disappears. When I press the switch, I create wind at the wall. When wind appears, wind moves right.
All right, so you get an idea, right? Like this, creating this small interactive
This is
simulation.
a second wall.
And you can progressively build more and more. There are some excellent examples, other examples, different types of simulations with different types of behaviors. Feel free to check out the paper for more examples. Also, you can create small games on the fly, only through sketching and narration. So in this paper, we talked about how to leverage speech and sketch together. But one of the limitations of the paper is that we haven't used LLM or any AI. That's why all the behaviors like verbs, adverbs, adjectives, they were all predefined. So which is why the designer's capabilities or artist's capabilities are limited, because there is a fixed set of verbs and adjectives and things you can apply to. So one of the potential of AI is that you are not bounded by these predefined verbs and adjectives and verbs. You can create new adjectives, new verbs on the fly because of its programming capabilities. All right, so let's get back to Feynman and see what's happening in the room. Looks like they're having conversation. Looks like they're becoming good friends. So, okay, the diagrams look slightly different. We have some writings. Looks like there's a set of rules. There is also a set of particles, different types of particles labeled. If we expand, we will see different particles. And there is also a set of interaction rules. All are inspired by the theories in theoretical physics. And as you can interact with it, when you bring two particles close to each other, you can see what are the different possible interactions happening. And all these interactions are generated on the fly by the rules governed by, specified by Feynman diagram. So you see, we have created a new version of Feynman diagram for a digital medium. And this is not a static version anymore. This is a dynamic simulation governed by these rules, principles, and a set of conditions. And Feynman didn't have to do programming. He used pen plus sketch to create this dynamic simulation. And lately, there are some excellent work in HCI about how AI can be used to create dynamic simulations for a variety of use cases, like social media simulations to real-time prototyping of interactive 3D walls. So just to show what are the exciting possibilities there for LLM to create this kind of simulations on the fly. All right. With that, let's move to next section. I love this quote a lot because it really talks about how different representations are dependent on each other, even though they're very different, even though they're very contrasting. So when Feynman first introduced Feynman diagram, as written by David Kaiser, the MIT professor, there was a lot of criticism, and other theoretical physicists were very critical about it. They thought the diagrams do not follow the rules of physics. They are incompatible with the mathematical expressions, and they were not sure whether it's a good tool for computations or not. But later, Freeman Dyson, who was a good friend of Feynman diagram, published this paper showing the mathematical, the equivalence and correspondence of these diagrams and mathematical expressions laid out by Schwarzinger. So you see, he actually laid out in this paper how different parts of the diagram correspond to different mathematical theories and mathematical expressions. And this really paved the way of the usage of Feynman diagram. It gave validation, and people started using it. So Feynman has learned his lesson from the history, and this time he doesn't want to make the same mistake. And he's thinking how to show that these diagrams are consistent with decades-long theories of mathematical expressions and theories of theoretical physics. He wants to show a clear mapping between mathematics and his pictures. But it's not obvious how to do that. So while he's thinking, let's take a detour and talk about similar problem addressed in HCI. This is excellent work led by Nazmus Saqib. This paper is all about, can we do mathematics with pictures? And can we do mathematics with both pictures and mathematical expression? And how can we bridge the gap? So the motivation of the paper is that, when you're a child, we start doing mathematics by, Montessori curriculum. We interact with these tangible blocks for different type of mathematical activities like drawing, counting, and then we do picture-based mathematics for counting and learning how to do multiplication, and eventually start doing mathematical abstractions and algebras. But as we move further along the right, we lose the intuitive underpinning of picture-based representations, and it is often it gets challenging for students. Now, here is an example, right? These are the same things, same math, but in two different representations. On the right side, you will see two buildings in UCSD. One is for students, and one is for teachers. And the problem is, what is the total number of students, people in that street, in that block, right? In the left side, it's the same mathematical expression, but in different form. So this prototype demonstrates how can we do both of them, how can we do mathematics with pictures and navigate between these different types of representation. So here you see that, the user Saqib is actually drawing a window, and then this window represents a room, right? It's very pictorial, but he turns this window into a list. So list means that there is nothing into that list, and now I drag students. There is all these students wandering around in the campus, and you can draw stick figures or in whatever way. And you can see in that room there are 4 people now. Now because it's a list, it's being dynamically updated. Then you can copy the number of rooms, and there are 4 rooms. Now you want to make a building, and then put all of them. And then the building is also a list that consists of another set of lists, and you can see all the counts there. Similarly, we are drawing another hostel for teachers, and then put all the teachers into that building. Now we have 2 lists, a pictorial representations. We want to do mathematics. We want to apply a mathematical operator. In this case, it will be a plus. So let's apply a mathematical operator, but in this case, we will draw a road. And then we will say this road is a mathematical operator. And in this case, it will be a summation. And everything we put into this mathematical operator will take the function as an input of that function, and it will create a summation. So that's it. That's pretty much our mathematics. But not only that, we can now navigate through different abstraction layers. So we can take each of the element, and we can say, OK, what is the mathematical representation of that? This is a hybrid representation. And this is like the mathematical representation, algebraic representation. Win equals to 4. Win is the name of the variable. There are 4 students. So that's why win equals to 4. And you can change the number, and you can change the values and whatnot. In similar case, this is the pictorial representations, and this is like a hybrid representation. You can see 20 students plus 15 teachers with rectangles. And then this is like just the mathematical expression. So this is, this is showing like how to bridge between pictures and mathematics, but through a very simple problem. But it really shows how children and others can do mathematics simply by drawing pictures. But at the same time, they can navigate through different ladders of abstraction to see what that pictures mean through mathematical expressions. And there are a bunch of other great examples in this paper about how can we do different type of mathematics and simulations just using this simple drawing. In this case, whether a subway map is busy or not, right? Because we have drawn a set of lists, and any point of time we can count how many subway maps are there. And all those maps are driven by simulation and data. We have just noticed, like how to map between different representations, pictures, and math. But this mapping is not always obvious. There is sometimes tension, and it's not obvious how to bridge one representation to another one. And that I firsthand noticed that tension when I worked at Autodesk almost 10 years ago. Autodesk released a tool at that time called generative design. It was a very powerful tool, but it took a set of forces like numerical inputs and then generate a 3D structure for designers. So it was a very engineering thinking, like you cannot sketch things. You have to have this very precise numerical input to get a shape out of it. But at that time, a lot of Autodesk designers really wanted to leverage sketching as a way to design and interact with this powerful generative AI tool. But it was not clear how to do that because sketching is very implicit in nature, right? It's like, it's not mesh. The numbers are not clear. So this is a picture, one of the first sketches of this famous architectural monument. It's actually Catedral de Brasilia, designed by famous Brazilian architect Oscar de Niemeyer. But look at the sketch, right? This is how ideas look like in its inception. In fact, he had many sketches, right? And it shows like it shows that he didn't know how many, what is the height of the structure, how many pillars will there be, what are the exact dimensions. He didn't know, and that's how ideas looks like in its inception. They're full of ambiguities and holes. And this is the precise nature of sketch. as Bill Buxton mentioned, that if you want to get the most out of Sketch, you need to have big enough holes. But the problem is that in this representation, Sketch is incompatible with explicit representations, because the moment we bring the sketches into CAD, we cannot translate it because it has to convert it into mesh. It has to convert it into precise dimensions, precise numbers, precise forces, and everything. But how can we make it work together? We'll work with two different representations in this hybrid medium. So you can see we will design a bike frame. Okay, you can design your own bike frame. So here we are designing, there's a mannequin there, and there will be a wheel. A bike definitely needs a wheel. And there is a handle there, but the handle could be, and there is a hole there. Yeah? There is an empty space there. And I have done some like rough sketches, and the handle could be anywhere within that space. I have specified a bunch of regions where the handle can be. So it doesn't have to be in exactly same space. It can be somewhere within that space. And also the empty space, the hole, is again somewhere within this space. So I have specified a bunch of possibilities. And you can see the sketches are imprecise. And there are many possible positions for the handle. There are many possible positions for the bike. Now, what we did is that for the generative algorithms, it also needs some sort of like data to calculate so that the bike frame doesn't break as we use the bike. So I've just exported a set of data and corresponded them. It should be able to carry a weight of this amount, and it should be able to carry a weight of this amount to the handle, and so on. So that is the input, a sketch input. Given that input, the generative design algorithm returns a set of possible bike frames. And these are some of the potential solutions. As you can see, you can navigate through all these different frames. And these are actually, if you can fabricate it. These are structurally sound bike frames. But what's interesting is that the translation bit happening between the sketch and geometry. So we had to compute some approximate geometry for the sketches so that we can feed it into the generative design. And the generative design returns this geometry, which we render in non-photorealistic scene in the context of a sketch, so that it's not returning just the final results, but it's returning something in between to give the designer ideas. So that's how the two representations are working in harmony with each other. And in case you are wondering how the bikes look like, I have also 3D printed them. Well, this is how these are exactly the 3D prints of those 4 bikes, by the way. But not in actual size, but in miniature size. All right, so back to Feynman. Feynman is supposed to do some work by that now. It's been a while. So, okay, so looks like Feynman is trying to draw some correspondence between the mathematical expressions and the animated versions and the static versions. And he used a clever technique, which is color, a specific design pattern used by some of the mathematics lately, to correspond different parts of the mathematics to the diagrams to the precise to the corresponding mathematical expressions. And there is some sort of transitions happening. So I must say this figure is pretty high level. In theory, you may need one or multiple layers of abstraction to navigate between this abstraction, but this is for illustrative purpose. And there is some excellent work lately, again, from colleagues like from Andrew Head, talking about how mathematicians are leveraging different kinds of design patterns to make math notations more easy and accessible. All right. So finally, at the end of section 2, we have these diagrams that, in Jeremy Brenner's famous cognitive psychologist's words, that are interactive, because you can interact with them, that are iconic, picture-based, that leverage our cognition about understanding space and time, and that are symbolic, that helps us to understand complex phenomena and do mathematics. All right, so with that, it's end of section 2. Let's move on to our final section, and I will see where I do that. Okay. So again, when you look at the history, we will see that when you look at the impact of Feynman diagram, it's not about just the design and invention of the diagram. Equally, it's how that generation of physicists were trained. So you have to design something and train the users who will put them into work. So a little bit of history there again from David Kaiser's book. Like shortly after World War II, Robert Oppenheimer, whom I know many of you might be familiar with for the recent movie, he hired a bunch of postdocs in Princeton University. And again, coincidentally, Freeman Dyson, who wrote the paper of Feynman diagram, how it is mathematically equivalent, he became the ringleader of those postdocs. And he did a lot of face-to-face mentoring to this new generation of postdocs to show how this diagram can be used, can be applied to different kinds of mathematical problems. Even Feynman didn't anticipate. In some cases, they had to change the diagrams. They had to change the rules to adapt it to the new problem set. So it really shows the power of like face-to-face mentoring and like training users. And at that time, they realized that just writing papers and tutorials were not enough for the spread of the tool. So now Feynman is about to share his document. At that time, 70 years ago, there was no tutorial, there was no YouTube. But he's going to share this diagram. But what is this diagram? It's not an app, it's not a static picture. It's not a software. There's a term for it. It's called personal dynamic medium. Like long time ago, Alan Kay introduced this term, and lately, Michel Bedouin-Lafon and others talked about web-straight shareable dynamic medium. So here, shared the personal dynamic medium with others, and a couple of days later, a postdoc been seen using that diagram. Well, not in the tablet, but in AR/VR. Well, with AI, you can ground how can you interact with a personal dynamic medium. And another postdoc later in the day is seen interacting with the Feynman diagram with his voice. He's asking what happens when a neutron turns into proton, electron, and anti-electron with voice, and gets an answer in voice. So this phenomenon of AI is called dynamic grounding, and there's some latest paper on this aspect of AI and some early examples of dynamic grounding about how users ground the interaction about how they want to interact with an artifact. And I encourage you to check out the work as well. And as they're interacting with it, they're also changing it, right? They're changing the rules because it's a personal dynamic medium. They're changing as they invent new types of particles and atoms, they're modifying the rules and updating the list. So here is an teacher who is trying to teach how this particle emitting energy and then again absorbs it, but he wants to use its own metaphor and storytelling, right? So, and then he says, okay, this is really hot day in San Diego, and someone decided to run without a T-shirt for a while, and then this is how the Feynman diagrams look like. So you see, this is the power of AI, and in a way, you can do something like this, not in this fidelity, with control nets today, where you can input a black and white video like the above, and get an output with a prompt like this, something like today in control net. So you see, it's malleable in different ways. You can put your own metaphors and stories into this diagram. By the way, this example didn't come out of the blue. I saw a video where someone used this analogy and I thought, okay, let's use this analogy. And this educator from London, I believe, was using this exactly same analogy to showcase how Feynman diagram works. So we have seen how these diagrams can be used, can be adopted to new context, and can be used in different kinds of settings and environments and interactions. And some of these concrete examples are showcased in this latest work led by Ryo Suzuki. In this case, this is all about how can we, integrate physics and math diagrams in real world with real-time sketching. So I will show you just a brief example here. Someone is drawing this line. This is real life. So this is like an iPad app looking at a live camera feed, and he's doing the diagramming. And the person has defined an angle, and then he gave the angle a name, and then defined a chart. And the chart has an x and y axis, and specified that angle he just defined will be along the y axis. And then as it is changing, you can see the diagram. So this is repurposing diagrams, mathematical and physics diagrams in real world, in the real time, right? So you can use a different physical objects in a very different environment, but render the diagrams in by doing real-time mappings. And there are some other examples about how these things works in practice. Again, with some real-time interactions, you can add up the diagram and create this diagram and showcase the diagrams in the context of real world. So in this case, someone is drawing and attaching a line to an object. You see the end of the line is attached to this object. And there's an angle defined, an angle is changing, but we define another angle, but that is independent. But now we say this angle is equal to that angle. And as we change this object, you can see the other angle is changing. And you can see, and in this paper, we have actually demonstrated how this type of like real-time mapping and interaction can be used for, physics experiment, explorable explanations, mathematics, and even other types of tangible interactions. All right, so we're almost at the end here. So let's reflect what Feynman did. So Feynman created a diagram which is very different from what he did 70 years ago. They are not static. They're designed for a dynamic medium. They are interactive and simulated. And then he also leveraged like different ladders of abstractions, mapping between different representations, which levers our different forms of understanding. And these diagrams are adaptable, malleable, personal dynamic medium, shareable with others that people can use their own way in their own context. And Jim and I talked about it a little bit as well today. So it's in a way, AI provide us, in Jim's word, a place for thinking, a tool for thinking. So last reflection. So what do you think? So let's see what Feynman has to say. So as a theoretical physics, imagination is hard because you have to imagine all these crazy things that you don't see, right? These subatomic particles. You have to imagine things. And very often the imaginations are very dynamic, or metaphors are very dynamic in nature. And being able to translate our dynamic ideas into this computer is powerful enough. And that's where AI plays a critical role. But most importantly, it has to be consistent. These diagrams, whatever we imagine, has to be consistent with everything else we know. And that's where the different ladders of abstractions, different representations, the mapping between them, help us to verify the idea, the diagrams in its inception. We can test them whether we are right or wrong. So these are real codes, but not in the context of AI, but in different contexts. But real codes from Richard Feynman. So finally, I mean, as I was thinking about this design fiction, I've been like I've been thinking about how software should look like, and there's like a great metaphor from Jeffrey Litt last year in a talk. He said that today's software building looks like we're building a gigantic ship with many different parts, like with designers and engineers, with deployment, testing. Software building looks like building something giant, but software building should look like something personal, like something like a lightweight bicycle, which is very lightweight, personalized. You can mold it, you can carry it anywhere with you. As I've been thinking about more about this design fiction, it's going back to decades old HCI's vision about personal dynamic medium that Alan Kay and Michel Lafon and many others, including Jim Holland and many others, have talked about for a long time, right? And I believe that AI is we are in a junction where AI has tremendous potential through their programming capabilities and multimodal capabilities to realize some of that vision. And the last couple of notes are, tools are not enough. We also have to train new generation of thinkers and creators, because if we look at some of the best inventions of cognitive tools, they have a certain way of thinking with ladders of abstraction, thinking with being able to come up with abstractions, being able to come up with great metaphors. And those are some of the things that we need to train ourselves. And AI will just facilitate that thinking, but it will not think for ourselves. All right, with that, I'd like to thank you everyone for being here. And I'd also like to thank you and acknowledge all the great students I worked with over the years in these projects. my collaborators and our dynamic abstraction group, with whom like many of these discussions were inspired by, many of the contents here were inspired in that group conversation. And also Rubaiat Khan, who is a PhD in theoretical physics, whom I consulted with. Thank you so much for your time.
Time for a few questions.
I love this talk. I guess one question I have is like, as someone who's like at Adobe and like building, like thinking about the next set of tools, do you see like existing tools that encourage these different dynamic abstractions and they're actively working on like actually scaling a lot of these things? Like what's stopping some of these ideas from actually being commercial today?
I wouldn't say anything is stopping. It's more like commercial interest, you know. I think many of the ideas we discuss has to come from academia, because these ideas are thought-provoking. They're driven by theories, but they're also like, we have to show that these ideas really work. Theory is not enough. We have to build tools. When there are open source tools, or there are some examples that these ideas work, then I think big corporations will be encouraged to think more along this line.
So I have a question. Like if we look at all the representations that we have in the world, writing and all kinds of things, it often takes us years and years and years to develop the skills to be able to exploit them. You know, so we spend a lot of years in school learning how to read and et cetera, et cetera. And those are incredibly powerful representations. But it sort of requires this upfront cost. You know, so if you imagine the space of all possible dynamic media, you know, how do you explore that space? I mean, what's a good technique for exploring that space if each one of those instances in that big space would require a long time learning it to be able to really, you know, be able to even understand how powerful it was? You know, it seems like one of the really hard problems. I mean, these kind of layers of abstraction are really good when we already have them. So like in time, we have, you know, all kinds of layers of abstraction thing, and it sort of comes with it. So we can do that kind of thing, or some of Haijun's kind of sketching things of moving up from, you know, just being bits to being, you know, something operating at a higher level. You know, so I just wonder, I mean, have you thought about that? I mean, it seems like one of the incredibly hard problems of.
That's an excellent question. Thank you so much for that question. And I think that's why I find the history of Feynman diagram so inspiring, that it took years of work to make this happen. And it's not by him, by others. And I'm sure there may be other representations, other inventions that we don't know of because it didn't pick up. And I think there is also this great paper I read a couple of months ago from Ian Araju about the history of programming. And there are like many visions about how programming should look like. And there are visions about programming should be more like mathematics, like algebraic expressions. And there are visions for programming should be more like typewriting. And typewriting owned because of a complex, you know, political and commercial reasons, because at that time we had typewriter, and there were commercial reasons to adopt that metaphor for programming. So I think there are many factors affecting when a representation is powerful and widespread. But fascinating questions. I love to continue the discussion.
So I really like the way that you talk about how like shaping how people think more than just giving them tools that can help what they do. So along those lines and along your answer and Dr. Holland's question, I was curious, like, how do you think that you can make tools like this so that help people to know how to approach representations themselves when they have a bunch of representations and they understand the representations, how to approach them with the extra level of expertise that you normally need to like be a designer or a cognitive scientist to pursue? Like, for example, to know that, say, maybe you have like, in the most simple sense, a mathematical one, like we have like Roman numerals, those are sometimes useful and they're sometimes not. Like what you showed in yours, like you could have a bunch of dots and like those are visual representations representations for quantity, right? Like tally marks, etc. But at a certain point, they become unwieldy. And mathematical representations, while they seem more unwieldy at first, there's a certain point where the numerals themselves become sort of more clear. So in that same sort of line of reasoning, do you think that it would be possible for an AI to sort of show people where the best representations out of their array of representations were, or given a representation that they're already using, suggest ones that could be better or more novel in terms of achieving their same goals using the qualities of the representations in mind?
That's a great question. I'd like to continue the conversation, but I think it really depends on the context and task. I think for different tasks, we will need different types of representations, and we will validate them in different ways. But I think what I really wanted to highlight here is that right now, inventing new representation in dynamic media is really hard because our imagination or our capabilities are constrained by existing softwares and tools that are designed by other companies, for instance. But I think the real power, and there was a great paper at UIST last year by Jing Li talking about how designers and engineers exhibit too much power over us because they decide how we interact with dynamic systems and softwares. But I think the real potential wanted to highlight is that moving forward, I hope AI will give us more agency to define our own normative ground, our own like vocabulary and language, and build new representations, which is challenging today.
Hey, I love the talk. So one thing that I was wondering is with the Feynman diagrams, and I think some of the research papers you're talking about, in some ways the representations are building on top of a way that someone is already thinking about something. So like Feynman was like really liked embodied thinking, and so in some ways I have to assume that the diagrams are sort of like a visual representation of that. Something like the energy brushes is like a similar thing where someone is already annotating images to talk about how to do these things. But the classic Roman numeral to Arabic numeral example is a little bit different because the breakthrough in the Arabic numeral notation is not just in terms of like it's a completely different kind of thing. Does that make sense? Okay, let me explain a little bit better. The Arabic numeral was not like instantiating something that people were already thinking about necessarily, right? It's just a different way of representing numbers that is just fundamentally kind of different, and it had a bunch of benefits that presumably were useful for accounting at the time or whatever. So I guess my question is like, how do we develop representations for things that we aren't already kind of doing in some way? That makes sense, which is kind of like more along the lines of thinking the unthinkable. Hopefully that made sense.
So can you repeat the last part of your question?
Yeah, so developing representations that are more along the lines of thinking the unthinkable, which is like very Red Victor kind of thing, where it's not just about like putting into visuals something that we're already thinking about, but actually thinking something entirely new.
Yeah. I would like to continue the conversation there to learn more about your questions. But I think what I really like to talk about a very concrete example. When we designed the energy brush paper, we had these primitives, but I wasn't even aware that there was like an animated version of that primitive, and the way artists used was so different. It was just mind-boggling, and they created the effects that I have never anticipated. So it really shows the power of malleable abstractions, like really how people take that inspiration, change it to something very different, and adapt it to their own needs. I think that's why malleable abstractions are super important. Yeah.
To expand on what I think you were saying, I don't know if I reflect correctly or accurately.
What does speaking do?
Do I need that, or can you guys?
It's recorded.
Oh, it's recorded. Sorry about that. To expand, I think what you're sharing is that AI can help us to expand our own creativity beyond what we already know about the universe and as it expands, et cetera. So I use the example of with folks that I lecture to and speak to in a startup ecosystem. Imagine being on the front of the James Webb, writing that around the universe and discovering things before they get beamed back to the planet. I'm thinking that's probably the visual you might consider when considering how AI might inform us about enhancing or expanding our own creativity.
All right, let's just end there. And thanks, Rubaiat, for this great talk.
Thank you very much. Oh, yeah, don't worry, it's not your fault. It's interesting. I mean,